This is lecture 15, chapter 5. In this chapter, we're going to talk about centroids, or commonly known as centers of gravity. And we'll be doing that for both 2D and 3D objects. And in our study in this chapter, we're going to limit it to just doing shapes, or I should say composite shapes made up of simple geometries. I know that you all have covered this in calculus in terms of using or calculating centroids using integration. We're not gonna, though there is a section on it in here, I'm not gonna emphasize that for time's sake, so that we can move on to things that are a little more challenging and more statics related. So the thing about this chapter is that I'm gonna cover it, and then we're going to jump into chapter 9 after just a couple of lectures here. And we're going to talk about what are called moments of inertia. And those are something that you'll definitely be using when you get to CE 204, which most of you will probably take in the fall, or also dynamics, where you'll be looking at things called the mass moment of inertia, which is slightly different. So, but having this background will definitely help. So let's first think about what is the center of area of an object. And so most of you can visualize that. It's where if you were to take the object to try to balance it on one finger, let's say it's a plate or just any object for that matter, where it balances on your finger is going to be the center of gravity, and where there's equal amounts of area left and right and equal amounts of area up and down. Now, this assumes that we have density that doesn't vary. And so we're going to assume that to start with, and then I'll show you how to calculate it if that's not the case. But again, we're going to stick to simple shapes. So we start off by, when we're trying to figure out our centroid, we divide our area into infinitesimally small elements. And then what we find is, and this equation's derived in your book, that the centroid is the integral of all the x locations with area divided by the total area. And so, and then the y bars is the same idea also. And again, I'm sure you've seen this before, so it should be review. Now, I think from a more practical standpoint, if we taking out the calculus, is just looking at the center of gravity. If we think about the problems that we did in chapter 3, where we had to balance the forces, or actually what we had to do is we needed to find the resultant for all the forces, and then find the location of where that resultant would be to represent those forces. So the top problem was the dock with 3 people on it. And then we found that if we sum the moments about the x-axis using the z distances, we could then determine what that was. If we did the same thing about the z-axis, then using the x distances, we could find that location. So this should be something that's, you remember that. And the bottom problem here is one that's in your book, and it's the same idea, is that you could add all those up, and you could determine where you could write an equivalent force and an equivalent location to represent those. So the center of gravity is the same thing. The only difference is, instead of having 3 or 4 or 5 discrete forces, we're talking about the forces over the entire surface. So for example, here we look at our plate again, just a varying shaped object, and we can take each little infinitesimal piece of weight, and we know that it has a certain x and y location on the plate. And as in the second example in B, you can see that there's 3 now. And so imagine that covering the entire plate. And so if you integrate all of those with respect to the weight and divide that by weight, then that gives you that exact x location. Now, I think an easier way to see it is looking at it like this. And so I'm going to show you, it's not very good focus. Might be a little better. I apologize. The focus on this hasn't been that great lately. So here we have our plate up top, and I have the different locations. And then what I've done is I've drawn this below, sum the moments about the y, where you take each x location times the weight plus each x locate the next x location times its weight, and then so forth. And that's just like we did when we found the discrete weights for, or the discrete forces on the previous examples. And we know that all of that is going to equal x bar times the total weight. And so remember how that was, this was the number we were looking for in those examples in chapter 3, and W was essentially the entire force or the resultant forces. And so again, that makes sense, because if we add up the entire weights of everything, that's going to give us the entire W. And so we do the same thing in both the y and the x, and we get this equation. Now, if we break this down, as I said, is that you have, we know that x bar times the weight is equal to integral of x over all dw. And so solving, we end up with this equation where we have the centroid of the entire object times the weight of the entire object is going to be equal to the sum of all of the individual centroids times their weight. And so you ask, well, how do you get those centroids? Well, let's think of it more on a macro level. If I have, say, a square and a triangle together, then I know that that square and triangle are each going to have a respective centroid. So what I'm going to do is I'm going to find the centroid of the square and the triangle, and I'm going to sum them, and then I'm going to sum the weight, and I'm going to solve for this. And this is ultimately what I want. So if we divide by W on both sides, this is actually our equation. And so it's the same for the y, works the same way. And if we were to go into 3 dimensions, we'd have the same thing, only it would be z. So one of the things to note too is I've been using weight and mass interchangeably, and that's reasonable because we're assuming gravity's constant. But another thing to think about is that we're also using center of area. And so again, unless the density is different, the center of mass, the center of area, the center of volume, the center of weight, they're all going to be the same. And in any kind of a geometric shape, they're going to be the geometric center. So if you have a cube, it's going to be in the center. If you have a triangle, it's actually, the center is going to be the 1/3 of the height. And if you look in your book in chapter 5, there's actually a table of centroid equations for different shapes. And so you'll need those to do the homework, and normally people ask, do you need to memorize them? Of course, you don't need to memorize them. If it was a lecture, you would need to memorize them, but that's okay. All right. So let's go back. So hopefully all of this is making sense. This is explained in your book in detail, but it's hard to, again, being remote, it's hard to get an emphasis for where the holes are in the knowledge base, because I can't see your faces and potential with those puzzled looks. So hopefully this is clear. So this is the table I was telling you about. I just want to show it to you real quick. This is out of your book. And so what it shows is if you have a quarter circle, half circle, or triangle, or various shapes, that you will have different X bar, Y bars, and it also includes the area for it. And then this is an extension of that table where you have the parabolic spandrel, general spandrel, and a circular sector. So again, if I'll try to limit any problems I give you to these so that you won't have to find some obscure geometry or shape, and that'll be the same on the final also. Now, one thing about a circle is if you have a quarter circle or a semicircular arc, that it's not going to have the same equation as a solid half circle or solid quarter circle. So you may have noticed that for a solid half circle or quarter circle, it's 3 pi over 4r, or maybe it's 4r over 3 pi. Sorry, I mixed that up. But point is that it's different. Whereas here you can see it's 2r over pi. And so let's go back just to make sure. Yeah, 4r over 3 pi, I apologize. So there it is, and 2r over pi. So remember, if you're dealing with an open circle, not a solid, then you need to make sure you use the correct equation. Okay, let's do an example. And this is a fairly simple example, but I wanted to do it. I think once you do a few examples, it'll make sense. And so what we have here is we have a triangle with a what looks like a quarter circle outside attached. So when we do something like that, the first question is, well, how are you going to do that with simple geometric shapes? And so what we can do, though, is we can subtract shapes away. And so, for example, if I look at this, if I added a square to this, an entire square, and then I subtracted off a quarter circle, that would give me the difference of this little this gray piece in here next to the triangle. So here's my shape. I want to find X bar and Y bar. I know that this distance is 120 millimeters. This is 75 millimeter radius. So what I was saying about subtracting is if I take the one triangle and I add a square and then I subtract that, then that's going to leave me with this. And that's all. So I just need to find the centroid of this piece, and this piece, and then I add them together using the equation I showed you. We're done. So here is my quarter circle, and I want to point out that for that, the centroid of that part, which is in the upper corner, is 4r over 3 pi. So it's important because depending on where the quarter circle lies in your geometry, say if this was flipped over, you have to always make sure that you measure from the actual centroid based on the equation. So normally if you downloaded the lecture handout 15, you'll see that I included a table at the bottom, and the table makes things a little easier for putting your values in. And so the first thing we want to do when we set this up is with the table is we find the area of each object. So what I've done is I've named objects 1, 2, and 3. So I know that the area of my triangle is 1/2 base times height. So 1/2 120 times 75. And so I'll just write down that comes out to 4,500. And I don't need units because I put them up here, millimeters squared. Now in terms of my X bar, actually let's just do all the areas first and we'll come back to that. Area 2 is just a square, so it's just 75 squared, gives me a value of 5625. And then the area of a quarter circle is pi over 4r squared, so 75 squared. And that's negative because it's I'm subtracting it off. And that gives me negative 4,418. So if I add this to this, subtract from that, my summation ends up being about 5707. All right. So we'll come back to that later because we'll need that. Now let's look at our X bar. Now for the triangle, X bar for a triangle is 1/3 of the height. And so 1/3 of the height, it depends on the reference point. So if I draw this like this, the height is always measured from across the hypotenuse. So like that. So this would be the height in the X direction. This would be the height in the Y direction. So 1/3 the height from here to here is 40. And since this is 120, this has to be 80. So 80 plus 40 is 120. So this is probably the only difficult part of doing centroids is getting the right location. And so we know that this is 80. So we'll go ahead and put that in here under X bar. And then for the next part, we know for our triangle, or I'm sorry, for a rectangle, we know that that's going to be just the center. So if it's 75, half of that is what? Half of that is 37.5. So 37.5 is the center plus the 120, because you have to go, whenever you're doing these centroids, you always want to go from your X and Y. This is your reference point here. So with respect to that, the centroid for this rectangle, or sorry, this triangle, is at 157.5. Sorry, it's a little squished in here. Okay, and then the third is, for the third, we want to figure out where is this quarter circle. So we know that X bar is 4 over 3 pi. And so we know that for X bar, the entire distance out to here is 195. So if this is 100, let's see, I need space to write. So we know that this distance to here is 195, correct? Based on this. So 120 plus 75 gets us out there. And then our centroid is this distance from here to here, right? So X bar. Now, when I drew this, I should have drawn for a generically speaking, this is X bar, this is Y bar. But in terms of our problem, this is the distance that we want. So I hope that wasn't confusing, but this is X bar and Y bar from the equation. So let's leave it like that, because we know then that if we know that the distance all the way out to here is the 195, then we know it's just going to be 195 minus this distance X bar. So the 4 over 3 pi gives us roughly 31.83. So we have 195 minus 31.83. And that came from distance. This is a lot easier on a whiteboard. So this is my X bar, 4r over 3 pi equals 31.83. Okay, if I substitute 75 in for that. All right, so I have that, I subtract it, and it gives me 163.17. So if I come back up here, I get 163.17. There, hopefully that made sense. So we have our centroid, our X bar for our empty area that we want to subtract. We don't make a negative because it's not negative. The location is positive. The only negative we use is the area. So now we do Y bar. So for Y bar, we know that the height of the triangle is 75. So we know that 1/3 of that is going to be 25. So we'll go ahead, put 25 here. And then we know that half of the height of the square, that's 37.5 down here. So that's just half this height of the square. And then lastly, we need this. So for that, that's going to be this Y height, this Y bar here. That's just going to be 75 minus 31.83, right? The entire height is 75, and this is 31.83, and we want this piece. So that's going to give us 43.17. So we come back up here, we have 43.17. All right. Little line there, sorry, tight. So once you have that though, everything is, you're pretty much done. The rest is just arithmetic, that's it. And so all you have to do now is you're going to multiply the area times x bar, give you x bar A, and then the y bar times area times y bar to give you y bar A. So I'm going to go ahead and do that. Let's fill it in. So this ends up being 360,000. This is 112,500. This is 885,938. 210,938. And this is negative 720,885. And negative 190,725. All right. And so the sum then comes from summing all of these. So we sum this column here. And if we do that, we get 525,053. And if we sum this column here, we get 132,712. All right, so that's the sum. So remember our equation said that x bar times the area equals the sum of the x bar areas, right? So x bar then is equal to sum of the x bar areas, right? Which is this, right? We had the x bar times A, we summed them. So we get 525,053. And we divide that by A. So we moved area over here. And that's just this 5707. And so that gives us the x bar equal to 92.0 millimeters. So if we did the same thing with the y bar, we get y bar equal to 132,712 over 5707. And that gives me a y bar and over of 23.3 millimeters. So that's that. So now you have the two. All right. So to quickly recap, you started off, you made sure that you had all your area represented by simple shapes. You found the area of each one. Any area you subtracted, you made negative. You found the x bar and the y bar, the center of each piece, represented to the x and y axis, or the origin. And then you just simply multiplied area times that, and area times x, area times y, you got that. Sum those up and divided them by the total area. That's it. So again, some of the geometries can be a little tricky, but beyond that, there's really nothing more to it in 2D. And when we go to 3D, we're just going to add another column for z. That's it. So that's this example. So let's go ahead, go back. And look at the next example. Now, I believe the previous example it wasn't on the worksheet. I think just these are, yeah. So we have this one, and a line I want to show you. So let's go ahead and do the parabola. And this one is very similar to the other one in the sense is that, okay, so let's look at our parabola. So we have the parabola shape, and then we have the circle. So here I've drawn it again. So we know that it's 3 meters high, and this focus is awful. Usually it's not this bad. So nothing I can do about it. All right, so the 3 meters high, we have this radius is 1.8 meters, and the distance from here all the way over is 4.5. So if we look at a typical parabola according to the equation, we know that its area is 4AH over 3, where A is this radius, H is this height. Now, and then if we want to know the center of it, it's respect to it being opening upward. And so y equals 3h over 5. So we, on the other hand, we're interested because this is our origin. We want to go up from this direction. So really what we're going to do is we're going to go from here down. So this part here is what we want. And so you can say that that's really just 2h over 5, right? Just 1 minus that, and that gives you this. So this is the equation we're going to use. Now we can calculate that really quickly because we know that 3 times 2 is 6, so 6/5 is 1.2. So our y bar is 1.2 for the parabola. And then our area, that's easy. Our area of our parabola is 4 times 4.5 times 3 over 3. So we get 18. And that's in meters squared. All right. So there's the parabola. And then we have, of course, have to subtract the circle from it. So we have, let's go ahead and go down here. So I've said area 1, in this case, I'm going to call area 1 my parabola. Area 2 is going to be my half circle. So I have that. That's going to be 18. My y bar is 1.2. And so we know then that if we multiply that, that's 21.6. So we got the parabola right off the bat, and then now we just have to do the half circle. So the half circle is easy. We know the half circle is just the area of that is just going to be 1/2 pi r squared. And so where r is 1.8, so that's going to be a negative 5.09. Okay. And then we need our y bar for it. And so in that case, we know that for this circle, we know that this here, what we're looking for is just 4r over 3 pi, which is going to be 4 times 1.8 over 3 pi, which gives me 0.764. So 0.764 here. Now, because the y bar is in the middle, I know that my x is 0 because it's symmetrical on both sides. So we don't even need to do it. We can just say x bar equals 0. Then you have to worry about writing it down. And so now we have our 4 over 3 pi. Again, this is 1.8. And so now if we add these, multiply this by this, we get negative 3.888. Add, and we get 12.91. And this is 17.71. And so therefore our y bar is 17.71 over 12.91 or 1.37 meters. All right. And so I guess sig figs there. So 1.370 meters, and that's our answer. So that's pretty straightforward. All right. Let's do another one and go ahead. And in this case, we have this shape. Now this one's a little more challenging than the past two were. Now in the context of this one is you have a triangle and you have, which it looks like a sector, but with this sector, you don't know the radius. So the radius, instead of being at the vertex in the center of the sector, you have it here. So what that does is it creates a slightly different challenge in that you're going to have to break this apart. You can't just use the equation for a sector and solve for it. That would not be correct. So I'm going to show you this, and instead of writing it out, I'm going to actually have it written. And part of it is that I'm not very happy with the focus on this thing. So that's too close. Bear with me. All right, so let's look at this. So what I've done is if you notice, and I use different colors to help you see, but I can make this triangle here. I know what this is. This is actually a right triangle because I know that this height is 60 and I know that this is 60. So these are essentially, here's half a square. And then I know that if I take this huge triangle and I add it to this sector, because then I can use the sector equation for that, and then I subtract off that triangle, then all I'm left with is this piece down here and that piece there. Voila. So I put the 3 here to represent the 3 here, but I'm going to call this whole piece 2. Okay? So when we do this, what we're going to do is we're going to first find the area. Now, for number 1, we know 90, 120, so 1/2 base times height gives us 5,400. So, and the y bar is just going to be 1/3 the height. So h over 3, that's 30. And then we can do that times that, we get 162,000. For 2, that part there is going to be using this equation. And so for a sector where this is R and this little angle here, half angle, is alpha. So what if the equation, and I would go ahead and look at this on your book, pause and look at your book, and you can see that for this thing, this alpha only represents half of it. So if you bisect this sector, and alpha represents that one angle, and then R is the radius, and then X bar is where that point is. And so for this equation, A equals pi r squared, I'm sorry, alpha r squared for the area. And then this y bar, which I'm saying y bar is the same as X bar because we're oriented differently, but this represents this distance from here to here is by the equation 2r times sine of alpha over 3 alpha, and make sure that your calculator is in radian modes when you do this. Otherwise, you'll come up with the wrong answer. So now now go ahead and calculate that. So here I have pi over 4, 60 times root 2 over 2. So that was my radius. And so my radius I know was, because of 60 was the height, I know that 60 times root 2 ends up being my radius. So if you think of the triangle, this is 45. If this height from here to here is 60, then the hypotenuse on a right triangle is just 60 times root 2. So that's where that comes from. So and my alpha, turns out that the angle here is 45 degrees, which is the same as pi over 4 in radians. So that's how I get that area. My y bar was calculated using this equation, 2r sine alpha over 3 alpha. And how I got that was that when I multiply 2r sine alpha over 3 alpha, I get 50.9299. So you say, well, 50.9299. So if we go back up to the original, we know that here is the x axis. So here's the origin here. So remember that this distance from here down is the 50.929. Remember, because it comes from the center point, or the middle out. So from here to here is 50.929. So I need the difference. So 60 minus that gives me 9.07. So again, 9.07 is the distance up to the centroid, because it's all relative to your axes. So then I just multiply that by that and get there. So last I have this triangle. I know it's 1/2 base times height. It's 60 high, so therefore 20 h over 3, multiply that. So again, once you figure out this, first off you have to figure out how to divide it. And there's another way to do this problem also, by making several triangles, and I see people do it that way. I think this way is a little easier once you visualize it. But so you have, once you find these and you figure out what you need to do, then just take care to use the proper equations, make sure your reference points are correct. So 60 minus 50.93, again, making sure I'm not blindly using whatever is spit out to me. It has to make sense in relation to the origin. So lastly, I sum everything up. I get this, divide by the total, and I get 18.95 millimeters. And so that 18.95 is from here up, which seems reasonable, about there. So if I'd gone from here down, then no, that wouldn't seem reasonable. But from here up, yes, that is. So again, always look at your answer, make sure it seems like that it's accurate from a real world perspective. As I said, I'll never give you anything that makes no sense in reality. There's plenty of that already in our world without adding it to statics. So, okay, so there's that. Going back. So one other concept in the 2D is the idea of a line. So line works the same way as it does with an area. The only difference with a line, is you'll find, is that oftentimes the center of gravity of a line lies outside of the area. So the center of gravity may not even be on the physical object itself. And that just has to do with the nature of considering this thing only to be one-dimensional. Or it's two-dimensional, but there's no thickness. So when we do problems with lines, it's exactly the same as before. There's no difference in the application. We still sum the lengths, and we sum the lengths, and then we find the x bar, y bar, and then that's it. So I have this one more example I want to do, and then that'll be it for this lecture. So here's this again. So I have my equation for my half circle, and I put that there because remember that for a half circle that is open, it's 2r over pi. So let's look at our three sections. We have a 6-inch line here, we have this half circle, and then we have 8 inches here. We know this is a 4-inch radius, and this is 30 degrees. And so, and here, maybe so I would try this on your own if you wish, just because to get the practice. So again, y bar is 2r over pi for the semicircle, and so I made my lines. L1 is 6 inches, the quarter circle is L2, and then the 8 inches L3. So let's look at my three sections. So length is 6, that's no problem. This is, remember, it's 2 pi r, so pi r for half a circle. That's just 4 times pi. And then lastly, we know that's 8 inches long. So then we come to our x bar and our y bar. Well, since our origin is actually here, then the center, the x bar, is going to be -4. It's going to be back here. And so it's going to be wherever this starts, because this it's considered, when you're doing centroids and lines, they have no, or sheets for that matter, they have no thickness. The assumed thickness is so much smaller than everything else that you don't worry about it. So that's -4. And then our y bar for that is simple. It's just halfway up, it's 3. And then the rest is just multiplying out. Then we get to L2, and we know we have the area x bar for L2 is 0 because it's right on the centroid. And the height y bar using 2r over pi. So that's just 8 pi, right? 4 times 2. So I left it in that form. And then I just multiply it out. So if I multiply this out, I get length times 0 gives me 0. And 8 pi times 4 pi gives me 32 over pi. Sorry about that. Oh wait, no, I'm sorry, it does give me 32. What am I thinking? I should trust my own numbers. Yeah, because the pi's canceled. So you have 32. And then L3, we have 8. And so the distance for that is 4 from here plus half of this. So it's, we know that the half of the length is 4, and then that length there would be 4 times the square root of 3 over 2, or 2 times the square root of 3. So I just know that cosine 30 is square root of 3 over 2, and that's why I did that. And then y bar is 2 because it's half the height. The height is a total of, I know if that's 8, this has to be 4. And so y bar is h over 3. And so what do I get? I have y bar equal to 2, which seems like there's an error there. Let me check something quickly. Okay, sorry about that. I fixed that. Glad I caught that. I know what I was thinking, but so if this is 4, then 4 over 3 is 1.333. So that's the y bar for that. So I fixed that. So if we multiply 8 by that, we get 10.666. And then if we add these, that's 50, and we get the total. So we divide that by our length, and we get 2.37. Nothing wrong with the x bar, so we divide that, we get 1.34. And there we have our answer. So that's the two values. We have x bar and y bar. So again, no different than what we did with 2D. So now I want to go on in the next lecture. That's it for this lecture 15. In lecture 16, we'll do 3D. And so there's not a lot of theory behind that because we already understand how we get centroids. The only difference there is that we're going to deal with one extra dimension. And the other thing is I want to also talk about the idea of different densities. And so if you have a different density, that's going to matter. Anyway, there was the problem. Should have shown it, but you had it on your sheet. Hopefully you printed it. All right, so thank you, and I'll see you at the